Hello and welcome back to another episode of the natural number game using Lean4. Today we'll be attempting the advanced addition world. So let's get started. So Peano's original collection of axioms for natural numbers contain two further assumptions, which we have not yet used in our game: successor injective and 0 does not equal the successor of a natural number. So let's start by adding those. We'll add our imports for my natural numbers, and we'll start by adding first lemma, successor injective, with, let's go back to our addition world to see what some of these things look like. Okay. We have A, B defined to be naturals. Successor of A to equal successor of B implies that A equals B. And let's figure out how to do this. Intro A, B, intro A. Oops, intro, I don't know, hypothesis. Okay, successor of A, successor of B, and prove A equals B. Not too sure. Okay, the reason, so for all A, we have both implications. If you put, okay, to work with these implications. Okay, so let me figure out how to use successor injective. Oh, so we can just do cases H. And then raffle. So cases H splits it into, what does cases do? So it's an inductive type, so we split it into some to different cases. So I guess the cases for H are just somehow this gets us to A equals A from H, because, well, H is an equality statement and it's also with natural numbers. Case reflexive. Yeah, okay, so I guess since successor A equals successor B, we have successor A on both sides, and then we have A on both sides, and then we can just solve it with reflexive. Okay. Yeah, I'm not too sure what cases H did here, so if anyone has a better idea than my botched explanation, please leave a comment. And now we're gonna solve 0 not equal successor. So we have lemma 0 not equal to successor for A, a natural number. We have 0 not equal to successor of A. Okay, can we intro something? Okay, so here, yeah, we intro that 0 does equal successor of A, and here we need to prove false from that. I wonder if I have anything in our addition world, it helps with this. Add associative successor add. Yeah, how do we prove that 0 is not the successor or something? Okay, in case does H trick do anything with us again? Why does that solve it? Huh? Not too sure what happened here, but cases of H seem to work. Case reflexive. Does that work? I guess with something with like implies false. Is before we had this, we need to get false, and if we try to split H into cases where with natural numbers, like successor of something is never 0. Not too sure. If I figure this out, I'll let you know, but for now I'm a bit confused. For now, let's just move on. Level 1 of the advanced addition world has been solved. Now let's do level 2, successor of injection. So we want to prove theorem successor injective A, B naturals with hypothesis successor of A equals successor of B. A equals B. Sorry. Okay. Let's think on how to do this. Can we apply successor injective? And then apply successor injective and exact H. Cool. I think we can also do repeat. Apply successor injective like this. Nope. That's fine. What's wrong here? Oh, I think the repeat was not a good idea. Lean is a little confused. Let me reload. Reload window. Let's see if this works. Good. Now let's move on to the level 3. Successor equals successor of equal. Okay, so this is theorem successor equals successor of equal. Then we have A, B, natural numbers. we want A equals B. It's kind of to imply that's weird. To imply successor of A equals successor B by what? So I'll do it like this. Start with the sorry. Oh yeah, this is intro H. Okay. So now we have A equals B, and then rewrite H. Ruffle. Great, that was very straightforward. Now let's move on to a different one. Okay, so now this is pretty easy. Successor equals successor if and only if A, B, natural numbers defined by successor A equals successor B if and only if A equals B. We know how to do this. Constructor exact. Okay, which one do we want first? We want this case first. AB. BA. Now what's wrong on here? Oh, this was the wrong one. Successor injective. Nice, and then exact. Successor equals successor of equal AB. Because this is for all AB, and we want a specific one where we use the A in here and the B in here. It's a little confusing because these both say A and B, but if I change this to like C, D, D, C, D, C, it'll be a bit more clear what's going on here. So this one uses A, B that we pass in. This one is expected to have type C of D, so pretty much substitute. Since it's for all natural numbers A and B, we say, okay, C is A, D is B to get this. C, D. Great. Add, write, cancel. Theorem, add, write, cancel, A, T, B, all natural numbers. I want to prove A plus T equals B plus T implies A equals B. Do we have something like this in the addition world? Let's see, A plus T, A plus B. With this, add associate, no, that's not quite right. Nope, nice. This is important then. How do we do this? Maybe with induction. Intro H. We have this. And we want to do induction. How do we do induction again? I kind of forget. Let's look at some simple induction cases. Okay, 0 add. So we do induction n with the 0 in the successor case. Here we do induction on C. So we do induction on a variable. Okay, let's do induction on T. Induction T with. And what do we write? 0 and the successor and the inductive hypothesis. Okay, 0, sorry, successor t prime, inductive hypothesis, sorry. Okay. What does this case look like? Okay, a plus 0 equals b plus 0. Can we just do reflexive? No. Apply, add 0. Is that not what that's called? Oh, we need the box. Rewrite, add 0. MyNat. It's not in MyNat, add 0. What isn't? Where is add 0? It is in tutorial world.lean. So we need to import mynat.tutorial world. Okay. I guess we can just import mynat.addition world to get both of those. Import mynat.addition world. Make sure you access to add 0. A plus 0. Okay, at h. Okay. Okay, now what do we have? Now we have, okay, let's do it twice, add 0, and now we exact h. Cool. How we're doing in this case? I think I should put this on one. Let's put it back. Let's do the dot trick so it looks a little nicer. That's not how that works. Whatever. Okay, there we go. That works. In this case, ooh, where our inductive hypothesis. Okay, intro. No. A plus t prime equals b plus t prime implies a equals b. Now what do we do? Okay, how do we? Okay, so we have our inductive hypothesis. We have our. Oh, can we assert a plus b? We can use a equals b implies successor of a equals successor of b. Can we use this at h somehow? Or I think we can use this on our inductive hypothesis. Rewrite this at h. Do t prime, t prime. Okay, let's see what that gets us. Did that do anything? Oh. Successor of t equals successor of t. That's not quite what we wanted. Oh, at h. At IH? Or I think I kind of want to do it at h. Oh, there's so much stuff going on here, I don't even know. This is something. I don't know if this is the right thing. I don't know why we have two cases now, case successor and case successor. this one has successor of t equals successor of t. Oh, well, that's, oh, wait, that's, raffle. Did I get rid of something? Okay, wait, can I do sorry, raffle? Okay. Now we're on one case. I got rid of both of them. Now we just have this case successor, or a equals b. How do we prove a equals b? I don't know if I made any progress. No, I don't think I made any progress doing this. Let's delete this. A plus t prime equals b plus t prime. Okay, if we could just get an a plus b t prime and a b plus t prime, we get a equals b. Okay. A plus successor of t, b plus successor of t. Oh, can I like work backwards? Let's see. Apply. No. Intro. Can I, no, I can't use my goal backwards. Okay, what I want to do is I want to say, oh, these are equal, so these become just plus t and plus b. So I thought it would be successor injective, which says if we have a and b, okay, wait, let's do this. Let f successor injective t prime t prime. Okay, what is f? F is the fact that successor of t prime equals successor of t prime implies t prime equals t prime. Can we like apply f? Wait, apply f at h, no, rewrite f at h. So that leads to this weird thing again. What is going on? Okay, h before was this thing. Well, successor of t equals successor of t. Oh, I guess, okay, I guess it's just saying that successor of t equaling successor of t implies t prime equals t prime. I don't know if that gets us the fact that it can like substitute. Okay, I need to think some more about this. Okay, after thinking about this some more, let's try turning h into something that has successor to turn it into a plus t prime, b plus t prime. So specifically, if we do add successor at h, well, once we have this, now we can let h prime equals add successor injective, which this is just a function that takes a, b natural numbers, and then an equality, and then it gets us a equals b. So our equality, so our eventual thing, is going to be h, and this just fills in the right things. So this becomes a plus t prime, or this is a plus t prime, this is b plus t prime. So We had IH, which is this thing, and then we have H, which is this thing, and then successor of that, and then here we actually just directly call the function successor injective, or functions proof. We have the isomorphism between those two, and then after that we now have this thing H prime. A plus T prime equals B plus T prime. Well, now we can apply IH to H prime to get A equals B, and that's what we needed, A equals B. And we're done. With theorem, add, right, cancel. Okay, let's move on. Add, left, cancel. Theorem, add, left, cancel. So now let's do A, B, T, or I guess T, A, B, natural numbers. We want to prove T plus A equals T plus B implies A equals B. So here we're pretty much like doing subtraction, but by canceling on the left then, right? What did I do wrong here? Expected command. Doing something here? No. Theorem. Oh, I spelled the word wrong. Theorem by what? Okay, so I think if we just rewrite commutative, so it becomes A plus T and B plus T, we'll be pretty much done. So rewrite add commutative. Let's just switch that back and forth. The second one we want TB. Great. And now we can exact add, right, cancel A, B, T, or ATB. Nice. And we've solved add, right, cancel, because I wrote here ATB. Sure. Great. We've made a solid progress into advanced addition world. We figured out a couple more axioms, and we wrote some theorems with implications. So that's the advanced thing. We have implications in our proofs, and if and only if proofs for our advanced addition world compared to our addition world where we only had equalities for all our different proofs. Thanks so much for watching, and join us next time where we do some more levels in the advanced addition world.